Welcome back to Advanced Math. This is a video for you. I'm going to talk about section 4-2 today. And to begin our study of 4-2, I would like to do something with you that actually came from 4-1. And if you watch the second video from 4-1, we remember that the compound interest formula was P. That's that marker's not going to work. How about this one? P equals P naught times 1 plus R over N to the N T. Okay, and what I'd like to do is we are going to do a couple very specific examples that are going to lead directly into what is the main focus of section 4-2. I am going to we are going to explore a situation, and you may want to pause the video and make sure you have not you, Eliza, the people at home, pause the video, make sure you have a calculator handy here so you can play along with me. But we are going to invest $1 for 1 year at 100% annual interest. Okay, we'll just leave it there for right now. We're going to invest $1, so P naught will be $1. We're going to leave it invested for 1 year, so T up there will be a 1. And the interest rate is 100%. Incredible, right? So our interest rate, remember, goes in as a decimal. So 100% as a decimal, remember, is just the number 1. Now, the only thing I haven't told it, or we haven't discussed yet, is how many times per year this is going to compound. Well, let's start with a situation maybe where it compounds once a year. Okay. If it compounds once a year, the calculation would be P equals 1 times 1 plus 1 over 1 to the 1 times 1. Whole bunch of ones there, right? Okay, but if I simplify this, if I notice, I don't really need that 1 out there. It's just multiplying this this quantity by 1. But 1 plus this is 1, 2. So that makes 2 to the first power. So the answer here ends up being 2. So if you invest $1 for 1 year at 100% interest compounded once during that year, you end up with $2. Okay? Now, let's say that instead of compounding the interest just once a year, okay, at the very end, and you end up with, doubling your money. Let's say we compound it every month. Okay, so I'm going to replace, everything can stay the same, or most of the stuff can stay the same. I'm still investing $1 for 1 year at 100% interest, but it's the end, the number of compounds per year that has to change. So I'm going to change those to 12. Okay, so I'm going to put a 12 there, and we'll put a 12 right there. I know that's actually, okay, I've got those in the wrong order. I don't want to confuse anybody. So instead of putting 1 times 12, I'm going to put 12 times 1. Because it's the end that's 12. All right, now let's get our calculators and see how much we make here. So that's just a calculator entry. So it'll be 1 plus 1 over 12 raised to the 12th power. And I get $2.61.3. So with 100% interest now, compound once every month, so they pay you a 12th of the interest after the first month, then that additional money earns interest during the second month, and so on and so forth. You end up with quite a bit more money, $2.61. Well, let's consider an even better bank, maybe. In fact, like I told you in the last video, my bank does this. They compound interest every day. Now, what they don't do is they don't pay 100% annual interest. So let's put a 365 here, because there are 365 compounding periods in a year. And we'll put a 365 times 1 up there. Let's see what shakes out on the calculator here. 1 plus 1 over 365 raised to the 365 power. Okay, this time I got 2.714, so I'm going to put $2.71. Okay, so we make a little more if we go from compounding monthly to compounding daily. Now, how many times can you compound it every year? Well, you can compound it every second, or every millisecond, every nanosecond, every picosecond. Okay, yeah, we can divide the time up, in fact, into an infinitely short period of time. In other words, we're going to let n, the number of compounding periods, approach infinity. Now, I can't put an infinity in there in the calculator. Infinity's not a number, it's just kind of an idea. But we can let n approach infinity and see what happens. Okay, and you can do this at home. What you could do is, I'm going to do it with n equals 1,000. Okay, so I'm going to type in 1 plus 1 divided by 1,000 and raise that to the 1,000 power. And I got 2.7169. Well, we're not quite where we want to be yet. And believe me, there's a point to this story. Okay, you might not know this. My daughter, Eliza, doesn't know this, but there's a number between 1 and 10 that she doesn't know exists yet, but she's about to.
There's an infinite amount of numbers between 1 and 10, so...
Yeah, but you've never heard of this number, I promise you. So here's what I'm going to do. I'm going to do this one more time, and I'm going to do it with 1,000,000 compounding periods per year. So I'm going to type in 1 plus 1 divided by 1,000,000. Okay, and then I'm going to raise that to the 1,000,000th power. Okay, and I'm getting really close to where I want to be here. I got this time, with 1,000,000 compounding periods in a year, I got $2.71.8. Okay. Now, I don't know if you recognize this number. I don't have the whole number up here yet, but this is the first 3 decimals of one of the most important numbers in mathematics. Eliza, do you know what this number is called?
No.
Okay. This number is called E.
I've heard of that.
You've heard of that. Good. Congratulations. Now, so what I'm going to say is this. And I'm going to write this out using some symbols and syntax that might not be familiar, but I'll explain it, okay? It's going to be pretty easy. So the number E, first of all, is approximately 2.7182881828, blah, blah, blah. Now, let me assure you, E, it looks like the decimal is going to repeat. If you've got 18281828, it doesn't repeat. E is irrational, much as the number pi is irrational. Okay? Yeah, and so I didn't put E equals this because E is approximately this. This decimal, the decimal places would go on forever without repeating. And that is E. And here is, notice we got to 2.718 by that compound interest example that I did before I erased it. But one way to get to the number E is we write it as this. And again, this is going to be unfamiliar syntax. The limit as n approaches infinity of the quantity 1 plus 1 over n to the n power. Okay, that's 1 plus 100% interest divided by the number of compounding periods raised to the number of compounding periods times 1 year. This is one way to arrive at the number E. Okay, let me tell you what this means. This means that n can never actually get to infinity. That would make no sense to say that. But as n approaches infinity, the value of this expression approaches the value E. Okay, we read this, the limit as n approaches infinity of this expression is approximately that number. Now, it turns out E And this is not the only way to arrive at the number e. E turns out to be incredibly important in mathematics. If you remember anything from Algebra 2, and I don't even know if you did this in Algebra 2, to be honest with you, e serves as a natural base for a logarithm. Okay, and as we'll see later in this chapter, since logarithms are inverses of exponentials, e also serves as a natural base of an exponential function. Okay, so let me clarify kind of the objectives here. Number one, we want to know that there's a number e whose value is approximately this much. Okay, it can be arrived at this way. Okay, among other ways. And e is going to serve as the base of the exponential functions that we're going to talk about in this section. Maybe we'll talk a little bit more about e. I don't know. I don't know how much you're interested in the number e. But it is embedded in the fabric of the universe, just like pi is embedded in the fabric of the universe. Nobody invented it. Now, Leonard Euler is the man who discovered it. Euler starts with E, and so that's, I think, how it got its letter, the letter that goes along with that number. Anyway, you are going to probably, the first thing you're going to do in the assignment is explore the function y equals e to the x. Well, notice that's structured the same way our exponential functions in 4-1 were. Remember, they looked like y, for example, equals b to the x, where b is just some constant. And in this section, we're going to say, well, that constant is going to be e. I just, why would anybody choose e as the base of an exponential function rather than an easier number like 2 or 3 or anything except an irrational number like e? Well, it turns out that the analysis of y equals e to the x is so much easier than y equals 2 to the x or y equals 4 to the x. And the reason has to do with calculus. And this may not mean anything to you, but the fact that e to the x is its own derivative makes the analysis of this exponential function a lot easier, okay, than an exponential function with any other base. Okay, so the first part of what you're going to do is you're just going to graph this function in the assignment and do some transformations with it using the same transformation rules that I talked about in 4-1. Okay, you're going to have to substitute some numbers in to this function and see what the output value is. Now, there are two ways to get an E on your TI-84. If you're looking at your TI-84, one way to get an E is there's an E right above the division key. So if you hit second and then the division key, that'll give you an E. But there's an even handier thing, or an even handier way to do it. Look along the left side, the third button up from the bottom is ln, natural logarithm. Right above that, there's an E to the x. And if you hit second and then the ln button, you get an E already with an exponent ready to be filled in by you. And since most of the time when we're working with the number E, we're going to use it as a base for an exponential function, it saves you a step, okay, of having to use that caret key to get an exponent up there. Okay, now, I think you're going to be able to handle all the transformations of the graphs of base E exponential functions just fine, okay, because the rules are the same as they were in section 4-1. But what I want to introduce you to, and this is actually easier than the compound interest you did in 4-1, is the concept of continuously compounded interest. Okay, so we even earlier in this lesson and in the lesson yesterday, or from 4-1, we talked about compound interest and the concept of compounding interest, 12 times a year, 4 times a year, 365 times a year. And then we also talked about the concept of we can compound interest as often as we want to, on as small a time frame as we want to. And what continuously compounded interest is it's interest that's compounded every infinitely small unit of time. Okay, so even more often than once every nanosecond. Okay, the time. This is interest compounded as the time of compounding goes to 0. Eliza, you were giving me some signals there. What's going on?
Oh, it's just been 15, 21.
Okay, all right. Well, I'll try to do this pretty quickly then. So the formula for continuously compounded interest, like I said, it's easier than the normal compound interest formula, or the structure is less complicated. P equals P naught times e to the r t. The P and the P naught mean the same thing they did in the formula from yesterday. That is the initial amount, that is the final amount. Okay, you invest this much, you end up with this much. E is E, okay, the number that we talked about in this lesson. R is your interest rate as a decimal, and T is your time period in years. So, if say I was to invest $1,000 compounded continuously for 3 years at 5% annual interest. Well, how much do I end up with? Well, I put 1,000 in as my initial amount, e to the 0.05 times 3 years, and I enter that into my calculator. Let's see, so 1,000 times, and I'm just going to use the e that's right above the natural logarithm key, the ln, and then in my exponent I go 0.05 times 3, and I end up with 1161.83. Okay, so after 3 years of this, I end up with $1,161.83. Okay, that's going to do it for 4-2, I believe. Be sure to email me with any questions. Thanks and stay safe.